Hello everybody, welcome to the reinforced concrete design. Under the reinforced concrete design it says investigation of singly reinforced rectangular beam. The traditional design of the beam, you have the moment and use that moment to calculate the dimension of the beam and the sizes of the reinforcement bars. In the investigation is you already have that, and this is the process of calculating the moment capacity of the rectangular section of the beam, like this one here. This is the reversal of the design. Alright, in design you have the moment and you calculate the dimension of the beam and the sizes of the reinforcement. In here we have the sizes and cross-section of the beam. We have to determine the maximum capacity, moment capacity of the beam, and this process is called investigation. Okay, investigation. Let's start the investigation now. Right here. So we have the cross-section here of the beam already designed. It has 375 millimeter, the width of the beam, and the total depth of the beam is 650. The effective depth of the beam from the outer, the extreme fiber of the concrete to the centroid is 600 millimeter. That is a 650 minus 50, the concrete covering there. So D is 600 millimeter. This is a strain diagram. The strain of concrete EC, I call it E, this is epsilon, right? I call it E to be easy, simple. So EC is 0.003, that is the strain from the ECI code 318 recommendation. This is a usable, that is the usable, the last usable strain of concrete. That is 0.003, that is when the steel has yielded already. Alright, so and the stress diagram is right here. This is the Whitney stress block. The depth of the Whitney stress block is A, and the centroid location is A over 2 on top and A over 2 on the bottom. The centroid of the stress block. Originally the stress block is shaped like this. See the line there? And it is very difficult to calculate the A based on the curve of the stress block like here. So Mr. C.S. Whitney modified this original shape of the stress block to be more simpler, like rectangular shape. So this is now adopted all over the world and used in designing reinforced concrete beam. This is the original, and this is now the shape of the stress block in form of rectangular shape. It's more easier than this one here, the old one. So we have the concrete stress there, concrete force, and the tensile stresses right here. The capacity of the concrete capacity, strength capacity there, and the tension capacity of the steel is right here. And the tension capacity is calculated as the total area of the steel multiplied by the ultimate strength stress of the steel. The concrete is 0.85 times the concrete strength FC multiplied by A and the B. The B here is the width of the beam, and A here is the depth of the stress block. To start our investigation, we need to find one area of 1 bar. the area of one bar is pi d squared over 4. Substitute the value of the pi and the diameter of the bar. D is the diameter, and square that divided by 4. Substitute the values there in this formula here. You get 616 millimeter square. That's the area for one bar. Now for the from the stress diagram, solve for the internal forces. There are two internal forces here. One is compression and one is tension. The compression is carried by the concrete above the neutral axis, and the tension is carried by the steel below the neutral axis, the actual neutral axis of the beam. So the compression capacity is 0.85 FCAB. That formula there, right here, 0.85 FC times the B there is 375 times A. We're looking for A right here. So it becomes 0.85 times 28 times 375A. You get 8925 Newton times A. Here I express it in Newton because we're looking for A, which is in millimeter. So that is the compression capacity of the beam. Now the tension capacity of the beam is total area multiplied by the strength of the steel. So it's 4 times 616 times 3, 44.7 here. It's equal to 849,340.8 Newton. And since we're looking for the force, we have to change it in kilonewton. So divide this by 1,000, you get 449.34 kilonewton. So that's this tension strength of this cross section of the beam. Now the beam, the compression and the tension should be in equilibrium. Should be equal, so that they are in a state of equilibrium, so it doesn't move. So applying the static of equilibrium, the tension should be equal to compression. So therefore tension capacity is equal to the compression capacity. So substitute the values there. Now you can solve for A. Tension is 849,340.8 is equal to the compression capacity is 8925, and A, we're looking for A, and from this equation we can solve for A. You divide this by this, tension divided by the compression 8925, you get the A is equal to 95.164 millimeter. So now we have the stress block, the depth of stress block, which is 95.164 millimeter. Now we can solve for the compression strength. Compression force carried by concrete. You substitute the value of A from equation 1. Substitute the value of A in equation 1 to solve for the compression capacity. So 8925 times the A, 95.164, you get 849.34 kilonewton as well. So therefore the static of equilibrium works. They are supposed to be equal, so it doesn't move. There's no unbalance, so they are balanced, right? Alright, now we have the both forces now, the compression and tension, and we have the A. Now we can solve for X. The X here is the distance between from the neutral axis to the outer fiber of the concrete. Therefore, the depth of the stress block A is 95.164. Now the depth of the neutral axis X in the strain diagram right here is formulated as X is equal to A. Now we got the A divided by the B sub 1, the beta 1. The B sub 1 value is right here. It is depending on the strength that you use. The 28 MPa that we use here is equal to 4,000 psi. This is in psi, and these are the values of the B sub 1, the beta 1. Okay, for 4,000 psi, which is 28 MPa, is 0.85. For 5,000 is 0.8, and 6,000 psi 0.75. 700 psi is 0.7, and 8,000 psi is 0.65. Alright, so psi, and so it is necessary to know the conversion from psi to MPa. I do have video for that conversion from psi to MPa. It's a short video, but I think it is important for some. It's good to have it handy and easy. You don't have to calculate it again. I show the process of calculating there, from psi to MPa, so it's pretty clear. So now the B sub 1 here is 0.85 because we use 4,000 psi, which is the 28 MPa in conversion. Alright, now the extra here is A over B sub 1 right here. So X therefore is 95.164 divided by 0.85. You get 111.958 millimeter. Here. So we got an X there, which is equal to 111.958 millimeter. That is the distance from the outer fiber of concrete to the neutral axis between the two strains here, strains of concrete and strain of steel, epsilon s. So I call it ES to make it easy. Okay, now from the strain diagram we can solve for the strain of the steel, the ES. But in a triangular proportion, the AS here divided by D minus X, and the EC there, concrete, over X, equate both to triangular proportion. ES divided by D minus X equal to CC over X. Concrete is 0.003. Now from this equation we can solve for AS, the strain of steel. ES now is equal to D minus X times 0.003 divided by X. We have value of X, which is 111.958. So 600 minus 111.958 multiplied by 0.003, you get the strain of steel to be 0.01377. Take note the strain of steel here, it's only have 1 0. Alright, it's a 0.0 and then 1. Only have 1 0 here. Alright. Now to check if the steel has yielded, the strain of the steel should be greater than, ES should be greater than or equal to EY. When the steel is yielded, the steel has a tendency to harden, and during the hardening of the steel there is a strain, produces the strain called EY. This is the hardening of the steel, and it has a strain value there, and that value of strain there should not be greater than, should be less than the strain of the steel, so you can make an assurance that the steel has yielded, because without this the steel did not yield. Okay, so because of this, the hardening of the steel, and it produces the strain called EY. That is during the hardening of the steel, when the steel has yielded. This is the point after the hardening, is it yields again from here and then collapse. This is the tipping point of the ultimate strength of the steel. So the condition is the strain of the steel while yielding is supposed to be greater than the EY when the steel is hardened. Alright, so the EY here, the formula for EY is EY equals to Fy divided by the modulus of elasticity of steel. So therefore Fy is 344.7 MPa divided by the 200,000 MPa is equal to, EY now is equal to 0.00172, and this is less than the strain of the yielding steel. Alright, so the AS right here is 0.0 and then 1. That's greater than 0.00172. Therefore this condition is satisfied, and therefore since AY is smaller than AS, therefore the section is safe. And this means that the steel has yielded before crushing of concrete, which is the safe condition, as it gives warning before the failure occurs. So so we found that the beam is safe, and then we can go ahead and solve for the moment capacity of the beam. So solving for the nominal flexural strength of the beam can be calculated as by taking moment. The definition of moment is force multiplied by the lever arm. We have two forces here, the tension force and the compression force. We can take moment any of this, moment here or moment there, they're the same. We get the maximum, the nominal moment capacity of this cross section of this beam. So moment, we take the moment. So here I'll take the moment at the tension capacity and use the strength of the compression strength right there, the CC, which is CC here is same as 849.34. Okay, now taking moment at the tension capacity, CC, the lever arm of the CC is the effective depth of the beam up to the centroid of the steel, and minus A over 2 from the centroid here, the lever arm, up to the centroid of the steel, because we're taking moment here, right? So moment at tension capacity is equal to CC times the compression capacity times D minus A over 2 is equal to 849. Substitute the value of the CC there and multiply it by the effective depth minus the A over 2. You'll get the nominal moment capacity of the beam is equal to 469.190 kilonewton meter. So now we found the based on the cross section of the beam, and the number of steels there that's been designed already, right? We're investigating the moment capacity of based on this cross section that's been designed already. All right, this is called the investigation. Now we have the moment capacity of the beam is 469.190. Now you may be wondering, we have the moment capacity, but what is the span of the beam? Here's the answer. To determine the possible span of the beam, you need the following. Number one, you need a load to be applied to the beam, and possibly uniform load or any kinds of loads, any kinds of loading. And well, the slab is uniformly distributed load, obviously, and the beam is uniform load as well. For the beam is very seldom, and it's very rare occasion to have for the beam to carry a concentrated load. I don't recommend beam carrying a concentrated load, but usually the girder, the girder carries a column. Girder usually carries a column on top of the girder, and the girder is carrying a column, so that's reasonable. But for beam, more likely no. I don't want to put concentrated, but so usually it's a uniform load, right? So number two, for uniform load, use either the WL square over 12 for fixed ends beam and WL square over 8 for simply supported. So to have a span, you need a load. So for example, here now, factor load 350 kilonewton per meter. Total uniformly distributed load applied to the beam. And we have the cross section of the beam. We apply the load for this beam to find the possible span of the beam because of this load. So find the span L. Solution is the moment capacity of the beam that we calculated, which is 469.190 is equal to the WL square over 12 for fixed ends, and substituting value of the nominal moment that we calculated, equate that to the uniformly distributed load WL square over 12. We not manipulate this equation here, get L square is equal to 469.190 times 12. The 12 goes there, and the 350 goes down here, and that's why we have it here. So L square is equal to this. Since this is L square, we have to take the square root of this to get the L. So L now is equal to the square root of 469.190 times 12 divided by 350. L now is 4 meters. So therefore we have the L, 4 meter L span of the beam because of the load. It depends on the load. If you double this, the beam will be like 2. Right? So the span of the beam is depending on the amount of load that you put there, based on the cross section of the beam already that you have designed. So it's kind of checking your moment capacity of the beam you designed. The beam is really capable of carrying that moment there. So this is a good tool for the beam that's been designed, and then you check the moment capacity of the beam, and this process is called the investigation. So now actually this size of the beam is capable of, has a moment capacity of, can carry a moment capacity of 469.190. Alright, so that's the end of the video, and I hope you like it, and don't forget to subscribe. Thanks for watching. Bye.